can learn from.
So the next speaker is Andrew Lenhardt. He's a senior hardware engineering at Microsoft since 2017. And he is using compilers and language to bring FPGAs into the modern development environment, right? So Andrew, feel free to share your screen. Great. Okay, we can see your slides now.
Now you can hear me. All right. Okay, thank you. So I am Andrew Lenhardt. I'm working at Microsoft on bringing FPGAs into a programmable realm. And what that means, I'll get to in a second. By way of background, I come from a very compiler and systems background on the software side. So when I talk about FPGAs in the clouds, I'm going to primarily be meaning FPGAs as a core part of every server in a cloud deployment. And we're going to have several uses for them. So the question is, how did the FPGAs get there in the first place, right? What was the promise that people were willing to take a bet on them? And I would argue there's really a few key ones in my opinion. The first is to be able to continually improve the hardware, right? The deployed hardware. We have hardware in the data center for a long time. Applications change. We want to continually improve it. We don't want to patch around bugs. We want to fix bugs. We want new features in the existing applications, and we want to be able to port new applications to existing hardware. Most cloud providers are moving to a view that they want to own as much of the hardware and software stack they use as possible for all the same reasons. Now, maybe you operate in an environment where you know your requirements years in advance. We don't. So having a lot of flexibility in your platform so that you can evolve it as requirements change. I'm going to be very generous and say every 6 months, not every 6 weeks. That's fine. We have boards deployed for that. And because we don't necessarily know, we want to be very adaptive to business changes, we have to parallelize platform development and application development, right? We have to, we want to be able to be deploying boards with more loosely specified capabilities with applications that we haven't completely defined yet. And we don't want to wait, and we don't want to stagger those things, right? We really want to get hardware out and applications up and running quickly. So that's what we're trying to do. Now, I was talking to a major engineering group in Azure who has their own RTL teams because they're working on a large deployment. And we were doing a proof of concept of some classic offload things for part of their existing stack. And we said, yeah, we'll get you some hardware in a couple weeks. We'll do some preliminary tests. It'll take a little longer to bring up the drivers and integrate it with your stack. And they were dumbfounded, right? They said, what do you mean? Hardware, all of our hardware people and the hardware people we talk to ever say is no. So why is that, and what can we do about that? So I'm going to argue that one of the key challenges is reconfigurability. And this is a little bit of a strange claim since we are talking about field programmable gate arrays. Programmable is right there in the name, and we do in fact program them in the field. So how is it reprogrammability is the issue? Well, I'm going to argue that there's different senses of reconfigurability. And we're not going to teach the weaker argument to defeat the stronger here. We're going to look at what we really want in a configurable system. So the weakest, what I call weak reconfigurability, is the reductionist argument, right? We have something that we can change the configuration of so it behaves differently, right? We can program it. And that's true, but it's not that helpful of a bar, right? PowerPoint animations pass this bar, right? We can program anything into PowerPoint using animations. if you haven't seen this video, it's great, go do so. That doesn't mean that's really a reprogrammable system. I mean, it's technically programmable. So what are we really looking for? It's a more holistic approach to programmability. And I say that reprogrammability really is a property that arises from being able to actually rapidly program devices in a sane fashion, being able to deploy and maintain and debug. These are all part of what makes a platform programmable. And how we get there is we have a good ecosystem. And the ecosystem we're going to worry about here is tools and standards and languages, but that's just part of it, right? You also need good communities and good education environments and existing code bases, right? There's a lot of things that go into having a really useful notion of reconfigurability. So, the end goal of all of this is, to quote Learning Perl from the first edition, make easy things easy and hard things possible. Now, this is the second reference to Perl I've made. I'm not saying be like Perl, although, anyway. So I'm going to take us through a few things we see in our deployments, right? Millions of units over many generations, supporting quite a number of applications that are core parts of the data structure, right? What makes our life hard, or what are some of the things that make our life hard? So first is really lack of good languages. And what makes a good language, one of the more important things I argue is a notion of progressive complexity, right? The language you should be able to do easy things or non-optimized things quickly, but if you need where you need the efficiency, and once you understand your use cases or data access patterns or whatever, the language should have, be rich in lower level details that you can start digging into and get rewarded with better efficiency, right? So if I spend effort optimizing this thing, I have a reasonable payoff in terms of the metric I was trying to improve. But the point is, I don't need to go through all of the low level effort for everything up front, right? I can start easy and I can optimize as I need. A good language, and this is unsurprisable, also gives you reusable, adaptable abstractions. And abstractions is a very broad spectrum. It can be a service, a library, a type, a synchronization mechanism, right? These are all very different levels of complexity for an abstraction, but abstractions are very helpful, and all of programming is building up abstractions. But what we really care about here is the reusable and adaptability, right? We need to not just be writing one-off things for this particular application on this platform. And one of the ways we get there is a good language has very rich parameterization mechanisms. And parameterization, like abstraction, is a spectrum. There's all sorts of types of parameterization, type-based, parametric, even a function parameter is a parameterization of some computation. And a lot of good application design is picking the right parameterization complexity for the problem you're trying to solve. And what those two things together let you build rich libraries. A good language has a very strong standard library of useful things that people often need. And it has a rich ecosystem of libraries that you can pick up and use. We'll get back to this in a moment. And one thing that is near and dear to my heart, having been in the Verilog world for a while now, is concise expression. Right? How easy it is to understand what code is doing has some strong correlation with how much of it you can see on your screen at once. And we'll also come back to this in a slide. And this one is also really important to our use cases, and I would argue a lot of use cases, is that the languages need to be cross-platform. They need to be standards-based, multi-vendors implementing the language, implementing the whole language, or The other successful mechanism is, an open language with a single implementation that everybody uses. Right? We can't have divergence between what different vendors support. So going into more detail on a few of those points, on the verbosity issue, I was looking at our code base and I started classifying, hundreds of thousands of lines of code to figure out what we were spending our bytes on. And we'll be slightly, I hope you are as slightly concerned as I am by the fact we have more blank lines than we have comment lines. Now, to be fair, that doesn't include comments at the end of logic lines, but we have some stuff. And then being very generous, we have a very small fraction of code that has any logic in it. Now, this doesn't include state transitions and stuff. So I went a little more detail to figure out what the yellow and gray are doing, right? What is our actual code in our applications? And more than a quarter of it is connecting wires into modules. A quarter of the code. Another 12% or so of that is declaring the wires in the module definitions to be connected to. And then, top level trivial assignments are another 10%. These are essentially connecting wires too. And what we're looking at is we're spending 10% of our code, hundreds of thousands of lines of code, connecting wires, not doing any logic, right? This is incredibly verbose. There's verbosity other places here, but this is staggering to me. So the next thing I want to talk about really is, and we've touched on this several points now, is a good standard abstractions or libraries, right? So what do we see in our development is a bunch of groups wind up building similar-ish sets of low-level components that they're going to build up their application on. And, these often are tied to vendor-specific pragmas or building blocks or chip-specific stuff. So they wind up having to be ported to every new platform. When that happens, the library tends to be diverge. It gets forked. That fork never gets merged back in. Where we're directly using vendor-provided things, they are different on every chip from every vendor, right? So we wind up having to do multiple levels of porting for everything. And then there's just a lot of human cost, right? Like having our developers switching projects have to learn a slightly different vocabulary for understanding what's going on. And we get embarrassing bugs that we fix on one platform, but because the libraries have been forked or diverged on another platform, those fixes don't get propagated. And we don't always even know all the places we need to propagate a fix because there's a lot of groups doing FPGA development. So what we really need here is a standard vendor neutral library. And it should give a bunch of useful components for us to implement in terms of that are provided by the vendors, but they have to have a vendor neutral standard and interface and parameterization. They can't behave subtly different between every implementation, right? And that gives, a good library gives you a lot of leg up on developing applications because you start getting a lot of free behavior. Right? You should be focused on your interesting defining behavior, not on standard data structures and modules. Another thing that hurts us is the lifetime issue, right? What does the lifetime of support for languages look like in compilers for the vendors that we use? And what we generally see is like each generation of chip has some compiler release, and maybe it's carried forward one release, but for all intents and purposes, right, there's a release of a compiler per chip, and then it's done. And that's bad enough. That gets worse when you realize that from generation to generation of the compiler, what you can synthesize changes. And it's worse than that. In fact, what the compiler will even parse will change from release to release, from vendor to vendor, from tool type to tool type. And this becomes a problem because now if we start looking at having 4 to 6 generations of chips from multiple vendors in production, and we're trying to target applications at all of them, as well as several generations in development, we wind up having to find the intersection of the language subset that all our tools we have to use for that set of things support. And, side note, the fact that the current system Verilog standard doesn't have a standard for what should be synthesizable, right? Old Verilog standards did, is kind of absurd, right? It just says every vendor can do what they want. And this is really painful. As a way of a counterpoint for this talk, I took some good C++20 code, right? Very modern standard, used some new features and new libraries, and I compiled it on standard GCC for the alpha. And it worked. I could use a modern language for something that's not been around for a long time. And I did the invert, right? So I have modern language support on old architecture with modern compilers. So I did the flip, right? I took old code that worked back then, and I ran it on contemporary compilers, and I recompiled it with top of tree, modern GCC for the same architecture. And the results I got when I went through the assembly was better with the new compiler, even though the architecture has been dead, right? I was able to take advantage of new target independent optimizations that have come with the compiler to improve my old code base essentially for free on old architectures, right? And this is a level of support that we really need because we are running many generations of architectures, right? It's not one and done and then we move on. We have to support a lot. So as a more DevOps problem, compiler quality of implementation really matters a lot to us. So being very conservative, FPGAs use a sizable fraction of all the build resources within Microsoft, especially relative to how many engineers that's supporting. And there's a lot of problems. Performance has certainly been complained about before in this workshop, but that really severely impacts the kinds of development and test flows we can do, the granularity of what we can check. And simply because we have so many targets that we're trying to compile applications for, we spend significant engineering effort just to try to rein in that resource usage to get to the point where we're not yelled at by the engineering systems people. Like we spend a lot of effort doing this. And we spend a lot of effort working around behavioral issues with the compilers. I won't talk about those, but we need to really make sure that we are behaving in ways that give us reproducible compiles, give us stable tools to use, etc. So, the promise we were looking at is we have
Andrew, we are running out of time, so if you like to.
Yep. Yeah. So the promise we were looking at is we have this really agile hardware platform. We can adapt it as business priorities and requirements change. We can deploy rapidly. And what we wind up seeing, though, because of issues like these, is we're getting very ASIC-like timeframes. It's taking years to deploy new applications. Now, it's not all doom and gloom. Once we get applications out and we have a bunch of dedicated RTL engineers for those applications, we are able to regularly update them, but only slowly. So the hope is that fixing some of these core language and compiler issues, maybe we can get closer to the promise that got this kind of hardware deployed in the first place. So, thank you.
Thank you very much, Andrew. That was very insightful.